As I was preparing for the material for this talk, I tried to find some of the most useful points to cover for just about everyone here. I know we have different background, different skill set, and different roles to play in the company. If you don't find the topic or the content I presented to be deep enough for your interest, come to me afterwards and then we can chat. But from just this past 2 days in this conference, I noticed that there's a lot of interest in recurrent neural network and how they can be used and applied to different kind of a problem, because essentially what we see every day are sequence that's evolving, that's revolving around all of us all the time. And a lot of time, for example, like spoken or written language, that's definitely a sequence data. Without knowing the sequence, nothing would make sense in that context. And same can be said to disease exposure and disease progression, as well as human behavior, as well as advertising trend and technology, and how we determine what customers' interests are at any given point in time. So I hope today's presentation will leave you a lot of room for imagination and creativity for your own line of work. But first of all, I'd like to thank these resources, especially Jason Brownlee in Australia. He is, in my opinion, one of the best authors when it comes to writing books about recurrent neural net, or LSTM in that matter. He doesn't come to the United States very often, but his books is definitely worth buying and reading, and I learned a lot. And then second is the GitHub post made by Tom Long and a bunch of Google folks. In fact, I'm going to showcase one of their open source solutions to help solving the problem. And I'm going to walk at a very high level how you can go home and download from GitHub their source code and start to play around and trying to fit it into your own LSTM kind of a problem. And then there's another resource that's also very valuable. This is where I learned about implementing seek-to-seek model using TensorFlow. And then next, I really have to give Google a shout out, because I don't think many people knows about this, but they do have a free, like completely free Jupyter Notebook environment for anybody with a Google account, with a Gmail account. And this is outside of GCP. As you know, GCP is not free. You get charged for hour, for resources and data transfer and so forth. But Colab as a Jupyter Notebook is definitely free. Okay, so I'm gonna have to give them a lot of shout out. And then finally, Christopher Colas, very famous LSTM log, and you're gonna see a lot of pictures that I just steal from his website shamelessly, and just because it's classic. And then also, I took Andrew Ng's course on Coursera regarding deep learning and LSTM, and those are definitely very helpful. And finally, in the past 2 days, I think some of you are also in the training class offered by Deleb and Brian from Jude Square AI Research. And two of them are definitely expert in this area, so feel free to reach out to them as well. And also, I want to give them a shout out for a wonderful training class in NLP using PyTorch. They're a great resource and great bunch of guys. These are some of the notebooks that I created and willing to share with everyone who's interested in seeing my code and how I implement some of the point that I'm going to cover today. And of course, that's my GitHub handle. So if you do a search in either Gist or GitHub, you'll find me there. And today's talk is going to be divided into 3 parts. Okay. First, I like to present to you a very high level of a customer journey problem and how historically, before the age of recurrent neural net, how do marketers, advertisers tends to think about customer behavior and importance of different touch point. And then the second part of it, I'm going to kind of introduce a little bit of domain knowledge and how I use domain knowledge to formulate customer journey problem into something like an LSTM or recurrent neural net problem. And then third, I'm going to go into a little bit of a deep dive into sequence-to-sequence model, seek-to-seek specifically. I won't show a lot of code, but there's some very important architecture information that I like to pass on to everyone so that as you start to learn about how to implement LSTM or recurrent neural net, you kind of have a good feeling about what are certain parameters mean and what are these cells doing when you're training them through gradient descent and so forth. Okay, let me start with a very motivating example. Sometime this year, I got a new iPhone. And how many of you have seen this kind of a notification on your iPhone? Yeah, quite a few, right? Yeah. So this didn't happen on day one. This happens about 2 weeks into my owning this particular iPhone. Okay, and then all of a sudden, once I get into a car and start to and turn on the engine and get ready to drive, I start to receive notification like this. 2 weeks later, 2 weeks after I got the iPhone. Okay, so that got me thinking: how does it know all of these things on the screen? For example, well, there's a timestamp. It's trivial, no big deal. But how does it know I'm going to work? And how does it know where my work is? Because it knows how long it's going to take if I take the best, shortest route from my home to work. So that got me very interested in what is iPhone doing? Is it tracking my movement? How does it do it, basically? Okay. So in order to do this correctly, iPhone must know where I am right now, my current place, and where I'm going to be next. And of course, it has to know what time of the day it is and what day of the week it is. For example, I don't see this notification on Sunday. Okay, when I get into a car and drive on Sunday, I don't see this notification. So how does it know? How does it know it's time for me to go to work? How does it know where I work? And how does it know I'm headed to work? Right? So this is kind of a question that was in my head. About 2 weeks later, when I start to see this kind of notification every day, pretty much Monday through Friday, every day I get into the car. So I start to make a few hypotheses. Being a data scientist as well as an engineer previously, I immediately start to think about, how does iPhone know this? How does Apple know this? So I plot out my daily route. This is my daily routine. I start off at home. I wake up, and the next thing I do, after eating breakfast and so forth, I get in the car and drive. And then I drive to office, and I spend about 8 hours there working. And then I drive again to the gym to do some workout, and then go back home. So this is my daily routine. This is my workday routine. And then I started to think about what could happen that triggers iPhone to learn something about my behavior. Well, I started to make notes of at least 4 things that keeps coming up. One is a location. iPhone definitely knows where you are because it knows it knows how to make a GPS call on your phone. So your lat and long is always known to your iPhone any given time. And then the second is a little bit tricky. I have Wi-Fi at home. Then once I leave home, my phone switched to cellular mode. So this is not pretty obvious to me, but I believe this is also one of the events that iPhone is keeping tab of. And then the third one is very important, which is a Bluetooth connection. Once I get into my car, my Bluetooth connection is automatically set so that my iPhone starts to be connected to my car. And finally, the timestamp, that's obvious. Bluetooth connection took me a little bit to figure it out as to what iPhone is really doing. Because if I drive another car which doesn't have Bluetooth, then I don't see this notification. So that's how I know iPhone is keeping track of all these events throughout the day. So what a software engineer immediately think about when they see a data like this is a state transition change. So it's got to be either all 4 or maybe even more data that I'm not aware of that iPhone is generating and keeping track of that causes iPhone to know that it's time for me to head to work as soon as he sees this time of the day, this day of the week, and in this particular car with a Bluetooth connection. So like I said, sequence model is in production everywhere, and iPhone is the best example. So this brings me to part 1, how a customer journey problem historically was being viewed and formulated. And you'll see some of the example here. For advertising, this is probably the simplest, but nevertheless, it's a table stake for any advertising agency or advertiser wants to know, which is, did you see my ad on TV, on internet, or did you click? And then also, did you visit my store after you see my ad? Yes or no? And this is the most elementary way, and it's still going on today for an advertiser to measure how effective their advertising campaign has been. Just looking at a confusion matrix like this can tell you a lot of information. And of course, you can really go to town with this methodology. You can do some kind of a Monte Carlo simulation, samplings, and draw different subset of data, and then generate some kind of uncertainty and confidence level. But in any case, this doesn't have any sequence or temporal event information presented to it. For example, how do we know these 10 people that saw the ad that made a visit to your store did not already visit the store prior to see any ad, right? So this is always a tough problem for advertiser to deal with, which is, what is my baseline store visit from these customers, these potential customers? In other words, if you go to McDonald's on a weekly basis, you're going to go there every week at least once. And just because you saw my ad doesn't necessarily imply that my ad was effective in bringing you to McDonald's, because you, like many people, probably go to McDonald's at least once a week, for example. So establishing baseline without a sequence in your data is actually very difficult for advertising. And of course, traditionally, they do a lot of holdout and different kind of a control group thing to make it worthwhile so that they can get by with some of the issues, such as how often did you visit in the previous month. So you got to do a lot of tricky statistics in order to control for these variables. Now, in the internet age, when we start to shop online, this is the kind of a customer journey that we typically see. And this is not a new idea, because internet is already more than 20 years old. So relatively speaking, internet and e-commerce and customer path in e-commerce shopping is not a new idea. And this book was written, I believe, at least 4 or 5 years ago, at least 5 years ago. It's called Web Analytic 2.0. And they have this figure. Some of these words, if you're not in a retail business, probably doesn't mean much to you, but direct just means that for this person, they just come to your shopper website without any evidence that they've been exposed. But in any case, what you can see is for any customer that come to your website and buy something, you can pretty much follow the cookie trail, the cookie crumb trail. So they start with organic search, and then they got exposed to your ad on social media. And then sometime later, they decided to come to your store but there's some heuristic involved so that you don't attribute this particular website visit to these exposure. So there's a lot of heuristic involved, but at that point, a lot of people in advertising world already realize that there's a customer journey problem, and a journey is actually a series of touch points that they can engage with customers if they do it right. They can bring the customer to click the buy button quicker than if they don't engage with the customer. So this is not a new story, but this is when people start to realize that we need to look at customer conversion or customer purchase behavior from a journey perspective. So now let's move to the media, TV, for example. And you can see the same thing. If I was able to measure whether or not or when you came to McDonald's or Home Depot, then likewise, I can also construct a customer journey, and different color indicates different TV networks of which that you saw the ad for McDonald's or Home Depot and so forth. So you see the problem is very similar. It's a sequential problem. Now, before the advent of recurrent net and the big data and the machine learning, this is how people typically think about determining which one of these touch points deserve the most credit for this customer, customer 1 to convert, as well as customer 2 to convert, as well as customer 3, customer 4. Customer 3 didn't buy anything. He just looked at different ads on different TV network all the time, and you never really see a label named conversion. Conversion really means click the buy button or buy something. Okay, so if you were to look at journey like this, what color is most important in bringing customer to the conversion stage? Well, there's a way to do it, and the most popular way is really the position base, which means that I'm going to look at first click and the last click, or first touch and last touch. It's a theory, it's a hypothesis. In the retail business, the first touch or first click and the last click receive the most credit. And then everything else in the middle in the customer journey will split the rest of the smaller or lower credit evenly. So a typical example is I give 40% to the first touch point, 40% to the last touch point, and then for the remaining 20%, I would split it among all the different touch points in between the first and last. So this is called position-based attribution model. So if you do this for every single customer that you have in your data, and then you aggregate it together, you will get a result that looks like this. 40%, for example. Okay, let me, I think I moved a little bit fast. Let's see, this has animation in it. Let's look at this customer first. You look at the data in which the customer actually made the purchase. There's a timestamp. And then you look back and all the data log here, where do you find the previous event from this timestamp for this customer? Well, then that's this one. Okay, so he was exposed to TV ad before this customer made the buy decision. And then you keep looking, and then there's a second touch, which is internet search. But the first touch is really the social network ad that the customer gets exposed to. So there it is. This is your first touch, this is your last touch, and then everything else is in the middle. So if you do the breakout for the attribution point, this says that 40% credit goes to social network, 40% credit goes to TV ad, for this particular customer to make the buy decision. So this is called position-based attribution. And if you do this for all the customers that actually came to your website and bought something, you will get aggregated data like this, and then you do the column sum, and then you can determine which one of the marketing channels carries the most weight. So this is a very popular way for the e-commerce, for internet shopping site in the old days to figure out what gets most credit in terms of customer purchase. But as you can see, the data structure, even though it's very simple, but this is a lot of work to scale. And if you decided that I'm going to add another advertising channel or more advertising channel, then you're talking about a lot of code changes, and it's not trivial, definitely. Right? Another way to look at customer journey problem is through a Sankey diagram like this. I'm sure some of you are familiar with Sankey diagram. The bar on the right, the height of the bar on the right indicates the number of people, number of purchases that's actually made. And then you trace back to each touch point. And then the thickness of each bar coming out of the touch point represents the size of the sample. For example, there are this many people in this channel when they're touched, eventually made it to the bias stage. And likewise here, and likewise here, and likewise here. So even though it's very pretty, but you cannot quantify it. You cannot make use of a data structure like this. It just shows you that there are customers that hops around different channels for the exposure before they made the buy decision. But over and large, some of them started to make the buy decision as soon as they saw the first touch like this, and they decided they're going to buy something anyway. But like I said, this picture, while it looks pretty fancy and it has a flow to it, the data structure itself doesn't really allow you to do too much or allow you to quantify a lot of insight out of this. So historically, these are the two ways that I know that in the advertising world, how people has viewed and trying to solve a sequential attribution problem. So now let's move into the TV advertising world. As you know, AT&T owns DirecTV. AT&T also provide mobile service to a lot of you. And like I said, like I alluded earlier, in a mobile world, your location is an open book to not only Apple, but also to different network providers, service providers all the time in order to make sure your cell phone is getting the best signal and hop on the most available bandwidth or band and so forth. So your location from the mobile set's perspective is an open book to service providers as well as phone builders, phone manufacturers. So it's not really a secret to company like AT&T or Apple for that matter, or Google if you use a bunch of apps. So this is the data that's going to be involved for me to build out an LSTM model to predict customer touch point and customer behavior. First of all, we rely on companies like Kantar and Nielsen to give us what they call the as-run log, which is nothing more than a schedule for advertising across the United States in just about every TV network. And from that, we marry that data with respect to set-top box log provided by the TV household that we have. We normalize the timestamp that way in order to determine which one of these set-top boxes was on when the advertising schedule was run. So that's how we know who were exposed to the ad and who were not from our cohort. And then on the mobility side of it, like I said, your location from a mobile phone's perspective is no secret. So we definitely know which mobile phones was at which part of the town in terms of latitude, longitude. And with the help of a place curation or POI database, place of interest database, company like Pitney Bowes, and there are many others that we also use, we can determine to a very good certainty whether or not you visited, say, a McDonald's or a Home Depot or any kind of retail store within some kind of a certainty. So again, determining visit and timestamp requires some kind of normalization here, but it can be done. And then we merge and order the data set like this. This is an example of one household or one customer, and the event actually is, I'm sorry, this is a 3 customer. Each customer can as you can see, can provide this kind of a sequence of events. This customer XYZ first got exposed to TV ad on this network, then this network, then this network. And then somewhere in between all of these exposure, there's a store visit that we made, that we made a determination of based on this part of the data. And likewise for this customer and this customer. So this is a kind of a data structure from the beginning that you can consider this as a raw data structure. We generate this data, and then we have to restructure it in a way that we can feed into a machine learning model. So what's the big picture so far? Well, can everybody hear me okay so far? Okay, all right. I just realized the microphone's been dropping on me. Okay. Advertising strategy will definitely benefit from knowing the favorable sequence and selection of channels, because like you see in this case, this customer visited the store even before he gets any exposure from any TV network. Whereas this customer gets exposed to these networks but no exposure. This customer gets exposed, had a visit, and it gets exposed again. So somewhere in this information tells you which network is more important than the others. Agree? So for an advertiser, it becomes very important to know what can I take away from all of these conversion or customer conversion sequences based on all of these exposure and touch point, whether it's before, whether it's after, or whether it's during their repeating visits, so forth and so forth, right? And knowing that, I can optimize my advertising strategy. Especially nowadays, we gather the data at a much quicker pace than what we were before. In the past, an advertising campaign typically runs on the scales of 4 to 6 weeks, followed by 2 to 4 weeks of post-campaign period to measure the residual or coattail effect of the advertising. That's the kind of a ballpark we typically deal with in measuring advertising effectiveness in the past. And what that means is you don't get the data until the advertising campaign is finished. And that could be either 8 or 12 weeks after you launch the campaign. But nowadays, we can collect data and curate data on a weekly basis. So we can definitely do a lot of campaign study even while the advertising campaign is being run right now. So we can make better decisions and optimize our strategy for the next week. If we already learn about certain customers, certain type of touch point exposure sequences is not going to be very helpful. We can adjust it later on. So now I'm going to move into part 2, which is formulate customer journey problem into the sequence-to-sequence problem that can take advantage of machine learning. So let me check my time. Okay. Looks like I got to move faster. So for the use case that we're dealing with, there are specific requirements. Before I talk about encoder-decoder, let me talk about the sequence padding. I think if you had an NLP training, padding a sequence would make machine learning much happy to go through the algorithms and make it more efficient and run it much quicker rather than have variable length when dealing with sequence data. So I'm not going to talk too much about that. It's a standard practice. And then for the heuristics, like advertising campaign, business unit has different kind of business rule that you can take advantage of as a matter of fact. So I'll show you a little bit of that. For example, arbitrary length of observed sequence as a cause, and then you just pad it. And then you predetermine what size of the sequence exposure you're dealing with. And probably 10 or 20 exposure is what we typically see, that we typically deal with. So again, heuristics. It's not bad. It's actually going to be very helpful to help you confine your machine learning models and data structures. the model success criteria, it can be very difficult, it can be very simple, and I like it simple. So I'm going to split a customer journey that I already observed up to this week. I'm going to split it in half. And I'm going to use the first half of the customer journey to predict the second half of customer journey. And my criteria is simply whether or not the second half of customer journey contains the word store visit. So we can skip over this. The data structure, I already mentioned this, so that you can kind of put it in a sequence like this. And like I said, this is one customer. He has 5 touch points in sequence. I'm just going to split it in half. I'm going to use the first half of sequence to predict the second half. And I have 50,000 customers. I can definitely build a LSTM model out of this. So now I'm going to talk about recurrent neural network. You've seen this picture before, but let me remind you that this is one recurrent cell unrolled in time domain. So you typically see a picture like this rather than this, but this is really one cell. So the problem we're going to formulate is really the sequence to sequence, like I said. I tried a very simple one, but it didn't work out too well. I think the sequence is much too complicated for me to categorize, as one kind of sequence will definitely produce a visit and one kind will definitely produce no visit. So if it was a binary problem, this would be nice, but the data didn't work out that way. It's much more complicated than this, so I have to use a sequence to sequence. And this is a very typical sequence to sequence model. The framework is called encoder-decoder. So this is your input sequence. For the customer that got touched by point A, point B, point C, I want to be able to predict point D, point E, and point F. So now let's talk about sequence to sequence model a little bit. And this is a kind of a data structure that we created. The observed sequence is like this. Every row is one customer journey. So this is just a Python. This is just a very standard Python list, and every element in the list is one customer journey. And once you split it into input and target, you split the journey in half like this. So it looks something like this. You have the first half of the customer journey and second half of the customer journey. And this is my training data. And here's a dictionary. And this is where business rule comes in very handy for my case, and I'm sure for your case there will be, because I don't have to deal with a very big dictionary. In fact, for advertising, it is already predetermined how many TV network I'm going to buy my time spot on. So you already know up front there should be how many TV networks in here, plus the start and stop token, and then the word visit also has to be in there, so you end up with this number of tokens in your dictionary. So this is the encoder-decoder architecture. Don't have to go through this too much. But what I want to remind everybody is it's actually 4 separate feed-forward neural network inside of the LSTM cell. Each one of these gates is actually a feed-forward neural network. So hopefully that makes it simpler for you to digest what LSTM is doing. It's nothing more than 4 feed-forward neural network, but unrolled in a time domain. And you're trying to find the best W that fits all your sequential data. So you're trying to find 4 big W's here. And so 3 of them are considered as gates, and 1 of them is a hyperbolic tangent layer. So this is where LSTM comes from. You have 4 gates and plus 1 hyperbolic tangent to do the internal state update. And each one of these is being learned separately as a feed-forward neural network. So this is the final data structure that's presented by my model. And you can look at my Jupyter notebook and you can take a look. But in any case, this is the kind of data structure I'm looking at. I have a holdout target sequence after I train a model that looks like this. And it has the target word visit in there so that I put a 1 and then 0 for otherwise. And then this is my prediction. And likewise, put a 1 if the prediction has a word a visit, and 0 otherwise. And based on this, I can build a confusion matrix like this. And in my opinion, the best practice for classification model is really to use recall, precision, and F1 for all of your classification cases. Because you're almost always going to run into data imbalance problem. And you don't really want to have to think about it too much. So one way to do it is really just to bite the bullet and then say, I'm going to calculate precision recall in F1 for each of the classification cases. And that way gives you an idea. Of course, it's always good to look at a histogram and spread of your data to know just where the imbalance lies. But during the model training as well as the model validation, it's very helpful if you look at each case separately so you have some idea. Like in this case, I learned that to be able to predict a successful store visit is actually very, very difficult. However, it is relatively easier to predict who is not going to visit my store after different kind of exposure sequences. And as you can see, the precision recall and F1 score for the negative case is actually much higher than predicting a positive case. So this is not to say that I can tell you who's going to visit the store, but rather this is at the higher level. This tells you how you can optimize your advertising campaign strategy based on your need. If your need is to go after these non-converters, then now you know who they are. And if your need is to keep pushing at these people that you think that they have a good potential to visit, but it just takes a lot of time for them to make decision because you haven't had the full sequence of event yet, then you definitely know who they are as well because the model keeps track of at the role level, which is the user level. That was the first one I created, which is using Keras bidirectional LSTM without any attention, without any embedding. So that gave me a baseline measurement as to whether or not this is going to be hopeful. So the next thing I use is a TensorFlow model. And with a TensorFlow model, I have an embedding layer in there. Data is not too different. So now I better move to the open source solution. And this is probably the best solution that I found, provided by Tan and a bunch of Google folks. And if you know how to do git clone, go ahead and do it. You can just clone it from this website very easily. And it's a bidirectional LSTM with attention built in. And they provide training, cross-validation, checkpoint, holdout score, all with a simple command line interface. So here it is. If you clone it, this is what I did. You just do a git clone. And then this is how you train. And it takes a little bit of reading their document to figure out what it means. But here's the attention model that they provide. They have another one, which I didn't try, but I just used their default. They have a file extension .in or .tgt, and this is where you should put the vocabulary data in this format as a prefix. So the file, the dictionary that you saw, is really written as a CSV, and plus the extension .in, and with the training data, development and test data, and then the out there is where the model, after you train and validate and cross-validate, this is where the model is, and then the rest of it is a hyperparameter tuning. Okay, so like I said, file extension to this is either .in or .tgt, and it has to be you can provide the path to it. And this is where you save the model. And let's take a look at the content of the format. This is my vocabulary that looks like this. This is my input sequence. This is my target sequence. And to score holdout data, which means you're going to call predict methods, this is how you do it. Mind you, this is a model we just created and saved out there. And the inference input file is right here, and the output file is going to be there. Again, this is where you have to specify the file extension. Otherwise, it won't know what file to look for. So this is a snapshot of some of the holdout data, the ground truth of it, and the prediction of it. So, like I said, you do the confusion matrix like you did before, you can get the same measurement as before. And this time, I think the measurement overall is slightly better in the positive case. Not much of a change in the negative case. But this is the best performance I got out of the 3 models. And just to check during the training process that your model is not just learning or memorizing, you always want to look at the training progress. You look at the loss function for the training data and the loss function for the validation data, as well as the accuracy. This is from TensorBoard, by the way, so it's readily available in there if you set up your TensorBoard and label your session name correctly in your TensorFlow code. And as you can see, within a certain epochs range, I'm hitting the best I can do when I look at the validation model. So this is where you should implement the checkpoint. This is why checkpoint is very important. And the TensorFlow checkpoint methods and the Keras checkpoint methods is slightly different, but format is not all that different. In the TensorFlow, you want to look up the train.saver class, and this is how you implement the checkpoint. At least this is how I implement it. Use the just use the best loss. Write the model out only if you have a better loss that beats your previous loss. And Keras, this is how it's done. It has to go through a callback interface or a callback method right here. And you first have to declare a model checkpoint object and pass it in there as a function here. So these are the lessons learned. You want to leverage your business rule to take advantage of it, to simplify your model so that you can train a model efficiently and you can simplify a lot of tasks without reduce the complexity in just the logic of your hypothesis. And the recommended classification KPIs are precision recall and F1 for each of the class. And you can look up how I did it by actually sklearn has a metric, and that's what I did. And in my GitHub notebook or IPython notebook, you'll find how I actually implemented it. So the conclusions are as such. The behavior can be modeled with LSTM and bypass a lot of issues regarding privacy. If you were to use some kind of a profiling data, CRM data, and you don't have to run into a lot of privacy issue because you're not dealing with those. You're dealing with a customer sequence agnostic to who that customer actually is and his or her profiles. The framework can support real-time as well as batch job. And also, this is a perfect model because tokenization and the vocabulary size is up to your imagination. So any kind of a customer event that you're interested in, you can always find a way to tokenize it with some kind of a code, some kind of a alphabet code or letter code and so forth. And then you can just use the LSTM model to train the data. So here again, here's my gist, and here's a resource, repeat it again. So if you have any questions, just shoot an email to me or look for me on the GitHub. So thank you for your attention.